In all these, they're real typical of the types of similar triangle problems that you're going to see. And often the triangles will be embedded within one another. Usually when that happens, it's pretty easy to use AA similarity because one set of lines will be parallel. They'll share this common angle, and then all you need is one other angle from each set to show that you have similar triangles. Okay? And so when you look to set this up, once again, my suggestion is take whatever the information is that you're solving for, begin with that as your fraction. So in this first problem, x is what I want to solve for. So x of the large triangle corresponds to what side of the small triangle? X is the base of that isosceles triangle, so is 4. Okay, and then you compare that to the ratio that you know. And so, Casey, what was the ratio of the larger to the smaller?
9.
Good. So you take this whole length, 9, over this corresponding length, 6. And now all you need to do in order to solve this is multiply both sides by 4 to get your x alone. And you can reduce your fraction. 3 goes into 6 twice, 3 goes into 9 3 times, 2 goes into 4 twice, 3 times 2 gives you your answer of 6. In problem number 2, it's a very similar way. You have a triangle embedded within another. Once again, they each have this 90-degree angle. They each share this common angle. So you have AA similarity here. When you're looking at this problem, once again, if you begin with your unknown, our unknown is x. X is this vertical leg, so it's going to correspond to the vertical leg of the smaller triangle, 9. And so that ratio of your unknown to your known corresponding pieces is equal to the ratio of the known horizontal leg of 28 and the corresponding horizontal leg of the smaller triangle, 12. And so once again, you can multiply both sides by 9 to get your x alone, and then just simplify what you have. Here, 3 goes into 12 4 times, 3 goes into 9 3, 4 goes into 28 7 times, 7 times 3 gives you your answer, 21. All right. Finally, this is a type of problem that you will see again and again. And that is if you wanted to estimate the height of a flagpole, and you could actually do this by measuring your own height and the length of your shadow and then comparing that to the length of the shadow of the flagpole. And the reason for that is you assume that the sun relative to both you and the flagpole is casting the exact same angle. This is called an angle of incidence, or angle of elevation here, sorry. And so this angle of elevation from the sun down is the same for both of these cases. So once again, you're looking at that 90-degree angle and then this same angle of elevation. And so you have similar triangles by AA similarity. And so the corresponding pieces match up. So if your height is your unknown, you could say that h, this vertical leg over the vertical leg of this triangle 6, is equal to the horizontal leg 27 over the corresponding horizontal leg 8. Set up and solve this equation. Multiply both sides by 6. And once again, you can simplify what you have. 2 goes into 8 4 times, 2 goes into 6 3 times. There's no other common factors here. So when you multiply across, you get 81 over 4. And then you can convert that into decimal form in order to solve.